Alright, today we're going to talk about the law of cosines, and as we discuss this we'll kind of figure out why there's another one, other than the fact that, well, there's a sine and there's cosine, so why not have a law of both. But specifically there are uses for the law of cosines that we'll talk about when we're solving a triangle. Let's go ahead and jump right in. The law of cosines is used to solve triangles in which two sides and the included angle are known, or those in which three sides are known. So if you have angle A, B, and C are the measures of the angles of a triangle, and sides A, B, and C are the lengths of the sides opposite those angles, then A squared plus equals B squared plus C squared minus 2 times BC cosine A. Now, easy way to remember this. I'm not going to, read out every single one of these because you guys can look at that and read and see the formulas. You can pause it and write it down if you want to. But here's the way you remember what you're doing and how this thing sets up. If you've got a side over here, you'll have one of the sides of the triangle, A squared. The other two sides are over here, like it's Pythagorean's theorem, plus some stuff. So you got A squared equals the other two sides, B squared plus C squared, minus, now notice what we've got here, 2 times B times C times the cosine of the angle opposite this side. That's all that is, and it'll be that way every single time. If you look at these down here, it's the same way. B squared, what's the two sides of the left? A and C, so they're squared and added together. You subtract 2 times the product of these two sides times the cosine of the angle opposite the side you're looking for. So what that means is the square of a side of a triangle equals the sum of the squares of the other two sides minus twice their product. That's the BC, AC, and AB, their product, times the cosine of their included angle. Now, if you draw out a triangle, here's the situation. B and C are going to be the two sides that make up angle A. That's what they mean when they're talking about an included angle. Now, if you're given two sides of an included angle, side angle side of an oblique triangle, none of the three ratios of the law of sines is known. So let's look at that just so you can see. If we've got this, we've got A, B, C. That's going to give us, this is side A, this is side B, this is side C. If we have side angle side, so that means we would have, let's say, this side and this side. There's my two sides, and the included angle would be this one. Notice you don't have ratio A for the law of sines. You don't have ratio C for the law of sines. You don't have ratio B for the law of sines. You don't have both pieces of information for any of those letters. That's why you would end up using the law of cosines, because the law of cosines gets you around that necessity. Now, in going to solve a side angle side triangle, you're going to use the law of cosines to find the side opposite the one angle you're given. Once you find that side, then you can go and use the law of sines, because you're going to have one of those ratios complete now. Now, you're going to use the law of sines to find the angle opposite the shorter of the two given sides. This angle is always going to be acute. Now, if you remember, when we talked about the law of sines, I told you that when you do the inverse sine, you're always going to get an acute angle. The inverse sine, when you go to find the angle in that direction, in that way, will never, ever, 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 ever give you an obtuse angle. And we're going to find out why that's the case when we talk about the unit circle, but that's the situation. So that's why you always want to get the shorter of the two given angle sides, because that angle is going to be acute. The law of cosines now does not have this problem. If you're finding an angle through the law of cosines, it will give you an acute angle, or sorry, an obtuse angle. The law of sines will never give you an obtuse angle. It'll always give you the acute angle that is supplementary to it, if it's supposed to be an obtuse angle. That's why you always want to do the shorter of the two, because there can only be one obtuse angle. So and it's always going to be opposite the longest side. So if you do the opposite of the shorter of the two given sides, you're not going to run into the possibility of the inverse sine giving you the wrong angle. Now, so you'll use the law of sines to find the angle opposite the shorter of the two given sides, and then you're going to find the third angle by just subtracting the given angle and the angle found in step 2 from 180 degrees. And then boom, you're done. So in some ways, the law of cosines work, the side angle side problems are a little easier. Yeah, you got the law of cosines, a new thing to learn, but it's not that big a deal. So let's do one. All right, solve the triangle in figure 615, that's this one, with A equals 60 degrees, B equals 20, and C equals 30. Round lengths of the sides to the nearest tenth, and angle measures to the nearest degree. So first things first, we know we don't have ratio A with our given information. We don't have ratio B. We don't have ratio C. So here's our side angle side again. And we see we have none of the ratios we need for the law of sines. So we're going to have to use the law of cosines. And we're going to find angle A. So A squared is equal to B squared plus C squared minus 2 times B times C times the cosine of angle A. And then you're just going to fill everything in. A squared equals 20 squared plus 30 squared minus 2 times 20 times 30 times the cosine of 60. So 20 squared is 400, 30 squared is 900, so we're going to get 1300 minus 20 times 30 is 600 times 2 is 1200. The cosine of 60 is 1/2, so 1/2 of 1200 is going to give you 600, which gives us 700. Now that's A squared, not A, so we have to take the square root. And when we take the square root of 700, we're going to get 26.5 once we round. So that's this length right here. All right, so at that point, hopefully you can see now we have one of the ratios we need to do the law of sines, and we can transition over to the law of sines now. And when we do, we're going to want to find angle B. So we've got sine of angle A, which is 60, over 26.5 is equal to sine of angle B over 20. Now, once again, remember, the reason I'm solving B is because it's opposite the smaller of the two sides here. So I know it's going to be an acute angle. Don't go by the drawing. The drawings are not always to scale. But opposite the 20 is going to be a smaller angle than what the angle is opposite the 30-degree side, or the 30 whatever side, 30 unit side. So now we cross multiply, and we're going to find that the sine of B is equal to 20 times the sine of 60 divided by 26.5 . And that's going to be approximately 0.6536. Now remember, that's just the sine of B. We want to know what B actually is. So we'll do the inverse sine of both sides. More specifically, the inverse sine of the 0.6536, and I get 41 degrees when you round it to the nearest tenth. So angle B is 41 degrees. So now we have all three sides. The only thing we've got to worry about is this right here, and 60 plus 41 gives me 101. If I subtract 101 from 180, that means this is going to be 79 degrees. Now, in this case, we had absolutely none of our angles to be obtuse, so it wouldn't have caused a problem. But if we had an obtuse triangle and we used the law of sines to try to find that thing, it would not have given us the correct angle. That's why you always are wanting to solve, and I didn't use the law of cosines or sines to find this one. I just used subtraction. Always find your acute angles with the law of sines. You can use the law of cosines to find the obtuse angles. It will give it back to you, but we'll talk about that in just a second. All right, so then we would list out all our information, and we know that side A was 26.5, angle B is 41 degrees, and angle C is 79 degrees. All right, now if you're given three sides of a triangle, solving the triangle involves finding the three angles. We'll use the following procedure. Now this one's kind of backwards. Before we were solving, I was telling you to solve the angle opposite the smallest side with the law of sines. Well, that's true. Here you're going to use the law of cosines to find the angle opposite the longest side. Now this goes back to the fact that the inverse cosine will give you an obtuse angle. So if there's going to be an obtuse angle, you want to use the law of cosines on it. It will actually give you an obtuse angle when you take the inverse cosine. Now, once you find the angle opposite the longest side, if it's not obtuse, then you know you're out of the woods. They're all going to be acute. Then you can use the law of sines to find either of the two remaining acute angles, and then the third by the subtracting from 180 degrees. So let's go ahead and jump in and do one of these. Now, also, it said to use the law of sines. You can use the law of cosines multiple times to find all these angles if you want to. But generally, the law of sines is a little easier, so that's why we say that. All right, so solve triangle ABC if A equals 6, B equals 9, and C equals 4. Round angle measures to the nearest degree. Now, if there's an obtuse angle, we know it's going to be opposite the largest side, so it's going to be opposite B. Well, here's the thing. You can rearrange these to get the cosine of B all by itself. And let me show you real quick. You got B squared equals A squared plus C squared minus 2 times A times C times the cosine of B. Now we want the cosine of B all by itself, so we're just going to get rid of all that other stuff, move to the other side. So we're going to move A squared and C squared. So we get B squared minus A squared minus C squared, and then that's going to be equal to negative 2AC cosine of B. And all these are multiplied now. So I want to get the cosine B all by itself, so I'm going to divide by negative 2AC. Now, instead of having the negative down here, you could go ahead and move the negative to the top and distribute it through. And what you end up with, and I'm going to rearrange this just a little bit, the cosine of B is equal to A squared plus C squared minus B squared all over 2AC. Now, you can rearrange every single one of those equations in the exact same way. Now we're just going to plug everything in and find what cosine B is going to be. So cosine B is a squared, a is 6, 36, plus c squared, which is 16, minus b squared, which is 81, all over 2 times 6 times 4. So the cosine of B is going to equal 36 plus 16, that's 52, and then we're going to subtract 81 from that. That gives me negative 29 on top. 2 times 6 is 12, times 4 is 48, so I'm going to divide that by 48, and that gives me a cosine of negative 0.60417. So I'm going to take the inverse cosine of that, and I'm going to find that I have an angle B of 127 degrees. So there's my obtuse angle that the law of cosines will find that the law of sines will not. So now once I know I've got my obtuse angle, which is always going to be opposite the largest, that's why you're doing the largest first with the law of cosines, the rest of them I can do with the law of sines and just subtraction. So do you want to find A or do you want to find C? Let's go ahead and find A. So we got sine A over 6 is equal to sine of 127 over 9. And we can do our cross multiplication and everything, and we're going to end up with the sine of A is equal to 6 times sine of 127 over 9, or approximately 0.5324. All right, and when we take the inverse sine of that, we're going to get 32 degrees. So A equals 32 degrees. All right, so at that point, we know that angle B is 127, angle A is 32. So all we do to find angle C is take 180 degrees and subtract the two angles we know. And we get that angle C is 21 degrees. So there is all of our information. So, not real tough, is it? Now, we've also got a formula that's kind of derived from the law of cosines, and it's Herons' formula. Approximately 2,000 years ago, the Greek mathematician Heron of Alexandria derived a formula for the area of a triangle in terms of the length of its sides. We don't have to worry about an angle at all. A more modern derivation uses the law of cosines and can be found in the appendix, but this one is the one we're looking at, the 2,000-year-old one. The formula for the area of a triangle with sides A, B, and C is the area is the square root of S times S minus A times S minus B times S minus C, where once again A, B, and C are the sides of the triangle. And S is 1/2 its perimeter. In other words, 1/2 of A plus B plus C. Now, if you want a proof of why this works, you can always go back and look. look online. There are plenty of places I'm sure that they prove it. I'm not going to prove it to you. We're just going to use it to solve one triangle. So remember, S is 1/2 the perimeter. So first things first, find S. So it's 1/2, and the perimeter is going to be 12 plus 16 plus 24. 16 plus 24. All right, 16 plus 24 is 40. 40 plus 12 is 52. Half of that's going to be 26. Now the area is equal to the square root of 26 S times 26 minus 12 A times 26 minus 16 B times 26 minus 24. Alright, so we got the square root of 26 times 26 minus 12 is going to be 14 times 26 minus 16 is going to be 10 times 26 minus 24, which is going to be 2. So we got 20 times 14 times 26. Right? So that's going to give us the square root of 7,280. So then we take the square root of that, and we get that it is 85, approximately 85.3. They want it to the nearest square yard, so it's just 85. And since the lengths are yards, yards, and yards, it's going to be square yards. And that's all there is to it. And that's, if you don't know any of the angles, then that becomes an easy way to find it, to find the area without having to find the angle. If you had that with an angle, it's another story. Let's say we have theta here, then we can use sine or cosine or whatever to find the height. But if you don't know that angle, this comes in handy because you don't have to worry about finding the angle. You can just use all three sides and find what S is. All right, well, that's all the law of cosines we're going to deal with. Remember, the law of cosines can also be used similar to what we did with the other trig functions in application problems. So if you got a triangle that's not a square, not a right triangle, you can still use the law of sines and the law of cosines to solve those things, to find all the different things. And there's some of the assigned problems that you're going to have that are going to be application problems. So you're still just going to apply the same concept, draw the picture where everything is, and go from there. All right, see you in class.